This is the second day of the LSI class. That's for the record. This is a solution of the first problem on the first homework set. It shows one of many ways that were turned in. I believe this one is due to Ted Kaler. This is a solution which, if you expand it to n inputs, the area grows as n squared, which most of them did. This one is fairly nice in that it's made only out of NOR gates, which is a fairly fast form of logic. There are many other forms with cascaded pass transistors, NAND gates, and so on, all of which are acceptable solutions. We're not collecting these or grading them, but if you have any question as to whether your solution is correct, please come by the SSL conference room this afternoon and show it to us. We'd like to help you figure out whether it's right. Were there any questions on this problem at this time? Anyone feel like they had a hard time? Pardon?
Will we get copies?
Yeah, copies of today's view graphs will be coming into the room in a few minutes, with the exception of this one, which got made too late. Let's go to the next slide. On the second homework problem, as I mentioned, there were many ways to approach a solution on this three-input exclusive OR function. This is one popular solution that many people came up with, where each input bit causes a pair of complementary values either to be passed straight through or to be crossed over. And then if there are an odd number of true inputs, those values are crossed over an odd number of times, which results in the 1 coming out on the bottom. I think I did that backwards. That may be the odd parity output, but in either case, it's very symmetric. Peter?
I'm having a little trouble seeing the color. The crossing over has to be done by sending one of the two down to the blue level, right?
Right. Crossovers are blue over another color, right? This one is not very well drawn. There's better ways of drawing that topology. I did this one in a hurry. Some of the other solutions look better. This is also the form that was implemented on a chip that was mentioned yesterday, that Hamming code error correction chip, which does like 6 and 7 input exclusive OR functions. And another solution to that is a solution that doesn't depend at all on the fact that what you're implementing is an exclusive OR function, because it's implemented with a 4-input multiplexer. This function block can implement any function by hooking its 4 inputs to various combinations of power and ground, and in this case, the complement and true value of the third input to that function. So as I showed you yesterday, you could do an arbitrary 4-input function with an 8-input multiplexer. And here's a way to do a 3-input exclusive OR gate with a 4-input multiplexer. This doesn't grow in any natural way to more inputs, however. Severa?
Is your game to draw inverters just sort of arbitrarily like that wherever you go? It seems to me that when you come to actually put them in, you have a certain amount of trouble, don't you?
You're right. This isn't really a valid solution because I asked for a stick diagram, and this isn't fully converted to sticks. This is mixed notation.
Well,
So,
no, but my question was a little bit more subtle than that. It's is it in fact okay to play this game? Obviously, one could then try to convert those the straightforward way to sticks, but in fact, you're going to get into trouble there because of the red lines.
That's correct. You can start off with a design like this, and then you have to try and figure out how to get the power and ground to those inverters, for example. And the problem's not finished until you do that, and I didn't finish it. So. Okay, are there any questions on that problem? Does anyone have a particularly interesting solution they want to talk about? Oh, on the first problem, be interested in knowing if anyone got a solution that grows only linearly with n. Several, yes. Somebody should come by and show us that this afternoon. We've seen a few, but is there a question back?
A smaller one for that one. Six transistors. But anyway.
Well, show us that later, too. Okay, let's get started on today's talk. I'm going to pick up this morning sort of where I left off yesterday and talk more about digital structures for LSI systems. Notice I'm not just going to talk at the lowest level of gates pass transistor logic. I'm going to try to move up to more interesting structures of logic to do more complicated functions. Was there a question back there?
Yeah, you have copies of the slides.
Copies of these slides will be coming in a few minutes, as I said. Barbara's producing the copies right now. Several of the topics we'll be covering today are arrays, which is a very powerful concept for making any kind of logic more structured. The topology of routing of power and control lines, data lines, and so on through an array. Regular structures for implementing random logic, such as read-only memories and programmable logic arrays. And special structures for highly functional arrays. We'll give you some examples of arrays made of custom cells. And I'll mention a little bit more about structured design methodology and the recommended techniques for designing large systems and containing complexity. First, let me just mention one thing that was left over from yesterday. I noticed on several of the homework assignments, people had a misconception of what you could do with switch logic. This two-input multiplexer, which is the basic, most commonly used example of switch logic or pass transistor logic, implements this and/or function. It is exactly equivalent to two AND gates and an OR gate. But that equivalence only holds because the two control lines are complementary. That is, there's exactly one of those AND gates which is enabled, and the OR gate effectively gets a logical output value because of that. Whereas in the general case, can you push the slide up, Doug? In the general case, if you're controlling this with two signals, A and B, if A and B are equal, then you're not going to get an and/or function. If A and B are both 0, the output is completely isolated from the inputs, which means its value will be whatever logic level was last stored on that node. And if A and B are both 1, it's even worse, because then both paths are connected, and if the inputs to that, the other two inputs to that and/or structure are not equal, then the output will be fighting, trying to go one way or the other, and it'll be somewhere in between, and therefore it's undefined. So when you build switch logic, this is something you have to avoid, is a switch path from a 0 to a 1, where things are somehow fighting each other. And you have to also avoid the temptation to use it as an and/or gate. If you turn off both of those outputs, you can't assume, both of those control lines, you can't assume the output goes to 0 as it would in the case of a true and/or gate. Several people made that mistake on the first problem. I think we got them straightened out. Okay. I can't hear you. I refuse to answer that question. Next. Let's say a word about arrays. This is an example that we touched on yesterday toward the end, is an array of shift registers. This effectively has an n-bit wide data path, or yes, in this case, an n-bit word, which can go through a delay of, say, m clock cycles. This may not be a particularly useful function, but it's the simplest way to illustrate the concept of an array. If you happen to need an m clock cycle delay for an n-bit data path, this is certainly an easy way to build it. This is built out of 2m n-bit half registers. That is, they're n bits in the vertical direction. There's 2m of these half registers. Alternate ones are clocked on phase 1, the others on phase 2. We just use this as an example, and I'll get more into it in a moment, talk about some of the advantages of the concept of an array. First of all, it's built out of a duplication of simple cells. You can see in the case of what I call a rectangular array, there's a basic cell, which in the case of a register, half register, consists of an inverter with a switch on its input. That's all it is, a very simple cell. And of course, it includes enough wires to interconnect with the other cells for routing of power and ground and clocks and so on. Arrays are generally built so that they only require connections at their edges. They're not very useful if you have to try and find a way to get wires into their interior. So by definition, we usually assume that an array only connects at its edges. And it's easy to express the design intent with an array because the array basically captures the essence of a large amount of logic in one small cell. And you say, give me n of these. It's like a very simple data structuring concept that programmers are used to, a way of organizing a large amount of stuff with a very simple structure. So that's the whole point of this, regularity. You get a lot of function out of an array with very little complexity. Okay? I'll give you some examples of sort of the topology of an array, how you go about getting the wires around, and so on. This shift register array that I just mentioned, this is one example of how you can route the wires in it. I've drawn the actual function in this array as simply an inverter, which is what it is. Although in many cases you'll have this same topology with more interesting function in the middle of those boxes. But the thing I want to convey on this slide is basically the routing, the directions of the colored wires. Notice the power is all routed on horizontal blue lines. The control signals, the clocks, are routed on vertical red lines, and those can cross without interfering with each other. And the data which is being piped through this thing is on green lines, as it has to be in order to be controlled by the red lines. And they do cross, and those are the clocking transistors. That's intersections such as this one. So it's very important that the direction of data movement be orthogonal to the direction of the control lines in most structures. The cell called SR cell, which is in chapter 4 of the book and is shown in great detail, which I'll show you here, is an example of a system constructed in this way. Notice also that the blue lines are alternately power and ground, and that the cells are in fact mirror images of each other so that they can share this ground line between these two rows, share this power line between these two rows. Let's look at the layout of one implementation of this concept. You haven't been introduced to layouts yet, except in a very cursory way. And we will, in fact, get into that more tomorrow to find out what the details are of how wide the lines are, how far apart they are, and what the various rules are. But you should know by now that a layout is just like a stick diagram, except the lines have been fleshed out to some non-zero width. The stick diagram on top here should correspond in a fairly obvious way to this layout, with the exception of some tricks in this vicinity, which you'll learn about later. Okay, you'll notice this has this wide blue line, which is the power line connected to this pull-up transistor. It has this wide blue line on the bottom, which is the ground line. It's connected to this pull-down device. This is the control gate where the horizontal green line crosses the vertical red line, which is the control line. Okay, this is just a very simplest cell. Now let's go to another alternative way of building that same array, just to show you that these things are not all predetermined. In this case, I've kept the horizontal flow of data on green wires, but I've put both the power and the control lines, the clock lines, on vertical lines, which in this case are blue. So that's quite a change from the last choice. Now, of course, a control line has to be red in some sense. It has to be able to gate the data. So the control is actually implemented by little red tabs coming off this blue control line, such as this one and this one. And that's clock phase 1. The power and ground are routed on lines parallel to that. I haven't shown much detail in the inverters. I've just drawn black lines coming out of them, connecting to the blue power lines to indicate that in some way they connect. Exactly what the detail of that inverter or other logic function in there is, again, not relevant to what I'm trying to convey here. So the point is, as in the previous case, that the data is orthogonal to the control. If the data runs horizontally, the control lines run vertically. This is almost always the case because they want to cross each other. Also notice that the data, the signals that you're controlling, are almost always run in green when they cross, say, the boundaries of cells in an array, because green is the level that can be controlled by a red line. So these decisions if you think about it, there's a few choices. And some of your choices are forced, and others you get to work with. Okay. There's another type of array that's very important, and that's a linear array. The one I just discussed is what I call a rectangular array. But one good rule of thumb you should keep in mind is that for every rectangular array, you're going to have several linear arrays, typically around its edges. This is an example that doesn't convey any function. It conveys just an idea of a floor plan of some kind of layout. It's got two rectangular arrays in red, and around their edges and between them it has linear arrays, which take care of feeding the appropriate conditions into the edges and grabbing the outputs and driving the control lines and all the various peripheral functions that you do around a big array. And notice that the two red arrays in this case are built so that they have the same pitch in the vertical dimension. That is, they match up with each other cell for cell. And because this is true, they can be interconnected. If not directly, they can be interconnected by a linear array between them, which simply takes care of maybe exchanging the order of some wires or changing the distance between some wires, changing colors or whatever. If those did not have the same pitch, then to connect this array to this array would require a different cell at each level to sort of fan the signals down and up. And that's often done, but it's certainly not as easy, and it requires the design of a lot more different cell types. It's a lot more work for the person doing the layout. If we had an easy automatic way to do that, maybe it wouldn't be so important. Okay, we have several examples of this kind of a structure. We'll be saying various things about the OM2 data path chip, which was designed at Caltech, with these kinds of considerations as a sort of a primary motivation for designing a highly structured machine. We'll draw various examples of functional arrays and cells from that machine. A simpler example of an array that has both rectangular components and linear components is a PLA, which we'll get into in a moment. It's a programmed logic array. But before we get into that, let me just give you an idea what a programmed logic array is good for. This is the old finite state machine. Many of you are probably familiar with finite state machines, typically drawn with a box of combinatorial logic and a register. Some of the bits that come out of the register are fed back to the input of the combinatorial logic. Those are called the state bits. In this case, I've drawn it with two half registers. It's the same thing, except that the input now is coming through a half register before it gets into the combinatorial logic, and the output is going through only a half register before it goes out. This can be rearranged in various ways, and in fact, you can put combinatorial logic between both halves of those half registers. You can put combinatorial logic in this lower path, in other words. There's various ways you can organize this, but this is a fairly simple model, and it fits the programmed logic array that I'll be mentioning here. The combinatorial logic in this kind of a machine is completely arbitrary. It just depends on what it is you're trying to do. It may be a controller machine, in which case it sequences through certain steps, maybe makes decisions and jumps into other steps. It may be simply an arithmetic function that has one bit of state, say for a carry bit in a serial adder. Maybe anything from very simple to a very complicated machine. So there's not much you can say ahead of time about what that combinatorial logic is. But we can say that a single simple logic structure, the programmed logic array, is often, very often found to be a useful way of implementing this. The programmed logic array, let me just introduce its dimensions. It's characterized by three things: how many inputs it has, how many outputs it has, and what are called product terms. Those of you who know about PLAs already know what that means, and I'll show the rest of you in a moment. And it lays out something like this. It's got two sections roughly similar, with red lines and blue lines and some green lines in there also. And they're sitting sort of at different angles so that the blue lines are vertical in one section and horizontal in the other. The size in one direction of those pieces is the number of inputs and the number of outputs, and the size in the other direction is the number of product terms. Now let's see what this thing does and how it implements arbitrary logic. It's actually nothing more than a two-level NOR gate structure, although I'll introduce it first in what's called the and/or form, which is this one on top. Anyone who's taken a course in logic design should be familiar with the fact that any logic function can be implemented as a two-level and/or function of its inputs. That is, it's equal to the or of the and of various combinations of inputs. And as this diagram shows, you can draw it that way, each output being the or of various of these terms. The terms, min terms or product terms, are the outputs of some AND gates. And you get to select whatever connections you like in this model to some of those terms to form your output. And you can generate those terms by selecting any combinations of the inputs. In this case, I've selected A bar and B bar as the input to that product term. I want to just point out that it's a trivial transformation from the and/or form to the strictly NOR gate form, the NOR form. That transformation only involves alternating the sense of the inputs. Since you have both A and A bar on the inputs, an AND gate converts to a NOR gate by inverting its inputs. So all you have to do is change the ordering of these rows and keep the connections the same. That changes the input side. On the output side, the only thing that changes is an OR gate changes to a NOR gate, which causes you to need to invert the output. Commonly, you'll need to invert the output anyway because of what you've chosen to implement in the programmed logic array. So I'd say there's no net disadvantage or advantage of one form over the other. They're sort of trivially equivalent. Let's look at what this thing looks like in a stick diagram, in an nMOS structure. This is a figure out of the book where I've gone over the green lines extra wide to make them show up well because they're important. Notice this one has three inputs, A, B, and C. Each input is shown coming through an inverter to drive this line, which would be A bar, and through this thing, which is an inverter without the bubble. That's just a buffer, a non-inverting buffer, to drive this other line. So the left half of this structure, the AND plane, has vertical lines representing all the inputs and their complements. Each horizontal line in this structure corresponds to one of the NOR gates of what we call the AND plane. That's the first NOR plane. Those gates are sort of distributed. I mentioned here, can you find the gates? If you remember the structure of a NOR gate, it consists of a pull-up transistor, a node, which is the output, and a number of transistors that connect that output node to ground. And that node doesn't have to be localized into a little box and called a gate. It can be distributed over the entire width of this structure. So, for example, the NOR gate here consists of this horizontal line as the output node, which continues all the way across this next plane. And these green lines that cross the red lines are switches to ground. Notice the vertical green lines in the middle are ground. The branches off of them are the legs in the NOR gates. So this NOR gate, in fact, has only one path to ground, which makes it a very simple NOR gate. Oh, excuse me. It in fact has three, which I forgot to highlight these other two. Okay? Excuse me for that. Let me just fix that. Okay. The top one, however, is in fact, as I was saying, has only one path to ground. And that's reflected in the logic equations for this structure. The product terms are defined by these equations on the bottom. Can you push that up some? It says that product term R1 is equal to the inverse of A inverse, which is simply A. If you pull it back down, we can see that better. Notice the R1 in the upper right corner labeling that first product term. And notice it has a path to ground which is gated by A inverse. Therefore, the value of R1 is the inverse of the input to that inverter, which is A prime, so it's simply A. Similarly, any AND function, such as these listed here, any AND function of the inputs and their complements can be implemented by simply placing these green lines. So the structure of this array does not depend on the logic that it's implementing. Okay, now on the output side, you have the same thing. Each output, Z1 through Z3, is defined by some equations down here. Those can be written in various forms, and it's easy enough to pick the placement of the green lines to implement that as a function of the product terms. In this case, they're written as functions of the inputs. To make it obvious how that works, you should write them as functions of the product terms also. Was there a question in the back? Yeah.
Non-enhanced horizontal lines are blue lines or are they green lines? I can't remember.
The non-enhanced lines are in fact blue. Those are metal lines.
Okay.
That's why they can cross both the green and red without effect. And don't fail to note the pull-ups on the ends here. Every NOR gate has a pull-up on the left end in this case. And on the vertical section, the pull-ups are on the top. So notice this concept of a NOR gate that's distributed over a long line. The pull-up can be almost anywhere, and the pull-downs can be distributed over quite a range. So it's really hard to break this thing up into gates, although logically and circuit-wise, it is exactly made of gates. Are there any other questions on the structure of this? Yes, Dave?
Could you make a PLA out of NANDs as well as NOR?
Yeah, I've seen attempts to make PLAs out of NANDs, right? There's no reason conceptually why you can't do that, but there's also no advantage to it that I can see, because NOR gates are almost invariably faster than NAND gates. Rick?
In speed and density, how does a PLA compare to a ROM?
We'll get into that in a moment, comparison of a PLA to a ROM. It's really hard to compare in general, but I'll say some words about that. I showed you before a PLA motivated by the combinatorial logic in a finite state machine. I don't want to get into too much of the details of how to design a traffic light controller, but that's what this is. It's a simple example of a machine that has 4 states. The 4 states are implemented by taking 2 of the output bits of the PLA. Let's just push the state table off. The 2 outputs, Y0 and Y1 of the PLA, which have already been gated by the phase 2 clock line into this output half register, are then fed back underneath the phase 1 clock line into this set of inverters as an input half register. So you see the PLA with its buffers already built into it, and with the inverters that you probably want on the output anyway, and the addition of some horizontal red lines, makes an entire finite state machine. You don't have to think about how to interface it to a register. The register is sort of inherent in the edge structure of the PLA. And the PLA is also nice in that the inputs and the outputs are on the same side, which makes it easy to feed them back. It's also easy to get the outputs out of the other side. If you take the pull-ups off the top row there and bring them down to the bottom, run the outputs out the other side, there's nothing to say that those vertical blue lines can't conduct the outputs in that direction. Ted?
Is it generally true that cells in PLAs are square because they have to match up on both dimensions?
Absolutely. The cells in here are square for exactly that reason. That is that the cells in this array should be identical to the cells in this array, and they have to be turned at 90 degrees, and therefore to have the same pitch, they are constrained to be square. That's a good point. Yes?
Is there any limit on the number of input terms you can have to a PLA?
As you increase the number of input terms on a PLA, The only thing that gives you any trouble is that the width of this section grows, okay? You may be using it fairly sparsely if you have fairly sparse logic. It may not be beneficial to let that double to handle twice as many inputs if you can decompose the problem in some way. But along with that increase in size, the metal lines on each of these NOR gates get longer. And as those get longer, there's that much more stray capacitance on those nodes, and so it gets a little slower. But what might really get you is that if the logic is complicated for that many inputs, then the number of product terms you need to design that function may grow also. So the thing may grow in both dimensions. And you can't really characterize it without knowing how many product terms are required for your particular function. And that just depends on the type of logic it is. Jeff?
Yeah. Are we grounded to the substrate there in a situation like this, or do we have to run another bus? Because it looks like we're trapped.
The question is, can you get ground magically here by burying a hole down to the substrate of the chip or something like that? And no, you can't do that. You have to, in fact, route the ground in there somehow. These edge cells typically take care of that by routing ground horizontally. These inverters and drivers all need ground anyway, right? And somehow you have to route it vertically through this section to pick up those lines, or pick it up on the outside edge. We'll show you some PLA layouts that show you how to hook up the ground.
How do you make the non-inverting buffers? Are those double inverters?
Yeah, to make this non-inverting buffer, you typically just take this output and invert it. And there are other ways which we'll get to tomorrow. Any other questions on the structure of a finite state machine as implemented by a PLA? I don't expect to spend a lot more time on this. There's a lot of discussion in the book about how to go about assigning the states and designing, by way of transition drawings and tables, programming this thing to implement the machine you like. But I'm talking now just about the structure of it. Okay? That was a traffic light controller that was developed as an example in Mead and Conway's book. And since it was in there and already programmed, I decided to go ahead and lay it out. And this is, in fact, one of the projects that we implemented on the last summer's multi-project chip. And it is the smallest project that has pads around it. And that's because in making a ring of pads, you can't very well get a hole in the middle any smaller than that. In fact, the PLA consumes about 10% of the total area of this project. So you can see it's fairly compact. It's got 5 inputs and 7 outputs in this case. And you can see the sort of regular structure of that. Let me just point out a few things in here. This is the AND plane, and it's identical to the OR plane in this case. I made them square so that, in fact, I have 10 outputs down here, even though only 7 are used. That's just because it was easier. These are pull-ups over here. There's, in fact, 10 pull-ups in 5 pairs, because that's the way they fit, and the same arrangement of 5 pairs of pull-ups up here. The input double inverters are down here. The input gets first inverted with this. Well, you can't see it very well, but it's just double inverters driving the vertical red lines here. And on the outputs, we have the phase 2 clock line coming in here, and then 5 pairs of inverters to half register those outputs. 2 of these bits are fed back in, just as in that previous drawing, into 2 input bits. This also gives you, a good feel for the scale of things. These big black blobs are the pads where you would bond wires down. I don't know if anyone is familiar with a 1 mil wire. We don't usually talk about mils, but wire usually comes in 1 mil sizes. It's about 25 microns in diameter. That is, the diameter is about 4 times as wide as one of the lines on this IC. And those wires mash down on these pads. These are about as close as you can get them and still be able to easily put wires on them. So that shows you that you can make sort of reasonable sized PLAs, and they really only consume sort of a corner of your chip. They don't make full-blown chips. Question, Ken?
Yeah, could you say what the other 9 clusters of stuff are
associated with the pad on the right at the bottom.
Oh, these things here?
Yes.
Yeah, this is something I alluded to yesterday, which is it's a multi-stage buffer which has the purpose of converting the sort of puny signal on these little lines in here to a big enough signal to drive something big like a scope probe on the outside or a TTL gate or something. So,
Receivers for one and
these are outputs and these are inputs. This structure is something we might get into later. It's a structure that we saw yesterday in a strange contact. It's a enhancement mode device whose source is grounded and whose gate is also grounded, so it's always turned off, as it should be. But it's a lightning arrestor. It's always turned off unless you zap it with a few hundred volts, in which case it quickly gobbles up all that current, protects your circuit. Okay. Let's talk about how big this PLA can get. The question of many inputs came up. If your logic is really nasty, you may need to decode a lot of product terms to implement the function. And the worst case, of course, is that you decode all possible AND functions of the inputs, all possible N input AND functions, which is 2 to the N different product terms. So you can see that it's not too good if a structure grows sort of exponentially in N, at least not for large N. It may be fine for small n. However, it may be just what you want. In this case, the AND plane is actually a 1 of 2 to the N decoder. So now you know how to decode N inputs into all their possibilities. You simply build the AND plane of a PLA, program each line for one of the possibilities. And this full PLA is exactly a read-only memory, or ROM. Here's what it looks like. Let's push that up some. The AND plane takes an n-bit input, which you can think of as an address, and it decodes it into one active line for each address. So if you have 6 input bits, there's 64 lines crossing there, and you have a 64 location ROM. And the action of that address line in the OR plane is to essentially read out the pattern of connections in this sort of programmable table, or this memory. It just remembers the pattern of connections and reads out one line of it. So this is a very simple read-only memory. And of course the question was asked, how does a PLA compare to a read-only memory for implementing logic? And it depends on how you think about comparing it. If you build a fully decoded PLA, which is this ROM, then it will in fact implement any n-input logic function, and by increasing the word width, as many n-input logic functions as you like. If you build a PLA, there's a good chance you can get away with fewer product terms, that is, less height in the structure. But if you go to change the program and suddenly find that you need more product terms than you designed in, you may wish you had used a ROM. Depends on how easy it is to change your design. So it's hard to say in general whether the PLA will be smaller than the ROM. Well, it's easy to say that in general it will be smaller, but it's hard to say if it's by any significant amount. One circuit I designed had 5 inputs. And by very carefully coding it into a PLA, I managed to get it down to 31 product terms. So used a ROM instead. Notice, however, the disadvantage of this structure. The address decoder, which is the AND plane here, is on the order of the same width, if the word size is comparable to the address size. It's on the order of the same width as the table that's actually storing interesting data for you, which is the OR plane. So it consumes about half the area and doesn't do that much for you. So on the next slide, I'll show you a somewhat fancier way to make a big ROM that doesn't have so much overhead. Here's an example of a 10-input read-only memory. 10 inputs come in here. And the concept we're illustrating here is called row and column decoding. You take the address and you split it into 2 fields, in this case a 6-bit field into the row decoder and a 4-bit field into the column decoder, or column multiplexer in this case. So now the total size of this memory wants to be a 1K by 8, as you see up here. That is, it's got 1,000 8-bit words in it, 1,024 8-bit words. But the row decoder only decodes 64 lines. Each of those lines, as it goes across the OR plane, is going to read out 16 complete 8-bit words. And those words are interleaved so that the first bit of those 16 words come out next to each other into this little 1 of 16 multiplexer. And the first bit of the word you want can be selected from those 16 by this 4-bit address into this multiplexer. So you get your first bit out here. This is a very simple concept. It's been used in integrated circuit read-only memories for many years. There's an example of this particular function, the 1K by 8 ROM in nMOS, on the board on the side of the room as part of the low-cost controller chip that was designed at El Segundo Microelectronics Center. It's built into a lot of Xerox machines these days. Notice if you estimate the area of these things just by counting sort of the width of this as 6 and this is 4, whatever, you can judge that the area, about 80 to 90% of the area is actually in the array that's storing the information. So there's fairly low overhead on this structure. Okay. Question?
Yeah, is the row decoder implemented just like the AND plane of a...
Yeah, the row decoder is the AND plane of a PLA. Yes?
Is there something done to make it run at a reasonable speed, since it seems to be driving 128 potentially 128 gates?
Typically, big ROMs don't run at reasonable speeds. They're pretty slow. I think they're often the bottleneck in a system. There are techniques for making it run faster. In fact, one of the techniques is to put a little bit more timing, have a sequence of pre-charge and then readout that can go on in that ROM. And I think Doug will mention that concept later of pre-charging has some speed advantages and power advantages. But you're right, the long horizontal lines that are actually reading out of that array are probably the speed bottleneck in that design. Okay, let me give a quick summary of techniques for combinatorial logic and finite state machines. For small machines, things with about 1 or 2 bits of state and simple logic, build them out of gates, function blocks, or small PLAs. Just as you would in TTL, you can build them out of, if you can do it in 3 gates or less, and 1 package, you might do it. Otherwise, you'd try and find an easier way, apply a little more structure to the problem. If you have a medium-sized problem, say a controller for a simple machine, then you probably want to use a PLA or something that you can easily change, because when you get into a medium-sized problem, there's less chance that you'll have it right the first time. You don't want to cast it into concrete if you have any chance of wanting to make changes. So PLAs and ROMs are very good for that. If you have a large problem, the PLA approach is just going to blow up. It's going to probably grow exponentially, as will the ROM. So if you have a really unstructured logic, then the big ROM is the best you can do. That sort of exponential complexity is inherent in a very random n-input logic function. If you can find a way to do it more easily than with a big ROM, fine. But a big ROM is very likely to be the optimum approach. If you have very structured logic, you have to take advantage of that structure. There's 2 ways to do that. Either your problem partitions into some way, it can be decomposed into medium-sized problems, which can then be implemented with PLAs or small ROMs, or some even simpler logic. Or you may have a structure such that it decomposes into a whole bunch of essentially identical pieces, and then you can build an array of that piece. This is a very powerful concept which we use a lot to implement highly functional arrays. That is, you design a special cell to do just what you want. You make an array of them to do something that's n times as good. in whatever sense your problem requires. Again, the low-cost controller chip, which is a Xerox microcomputer, picture of it over here on the red board, combines several of these techniques. It has big ROMs in it. It has a big PLA for the controller, which is essentially instruction decoding and state sequencing. It's got small PLAs for various other control tasks within it. And it's got some very complicated, sort of random-looking cells, which are then stacked about 8 wide to make things like ALUs and stacks. So it's got this combination of highly functional arrays, large read-only memories, and programmed logic arrays for controllers. And then they're sort of thrown down on the chip and interconnected in a not pleasingly regular way. And as an alternative to that, you'll see more in Doug's talk that you can design these pieces to fit together better and come up with something that looks more like the OM2 design, which is highly regular. Okay. Got one more thing to talk about, and that's as an example of what I call a highly functional array with a custom cell. Talk about a register file. That's a small random access memory. You can think of each single bit of this memory as being a small finite state machine. And so here it is. It's got these two half registers, the input half register bit and the output half register bit. Excuse me. And between those bits, the bus logic decides when to look at the bus connection. I'm assuming this is a register file connected to a bus. And that this logic, if a read is indicated, then it takes the output that's stored in this half register and sends it out on the bus. And if a write command is indicated, then it takes the logic value on the bus, brings it in under the phase 2 control and into this half register, and it recirculates. This type of register is called semi-static because on every clock cycle it refreshes itself, but if you stop clocking it, it's dynamic. It will forget eventually. Semi-static because no explicit refresh operation is required. You just simply have to keep the clock running. And then the read and write control lines control its function. Without going into the details of what the logic is in there, I think you can see that it's essentially trivial. And that if you wanted an array of, say, 16 words by 16 bits of this register, you'd probably work pretty hard on making that logic small, because you're going to have whatever area penalty you have in there, you're going to have it 256 times, if I did the multiplication right. Let me just point out that pass transistor logic is used for the bus read and write connection because you may want other cells to be able to read and write that bus also. RAM doesn't usually talk just to itself. The OM2 machine has a 2-port version of this concept. That is, the RAM cell that it uses has 2 inverters, and it's got some control lines and pass transistors and so on. And if you looked at it, you wouldn't think it would fit that diagram. In fact, it doesn't exactly, but it's approximately that. It's got 2 ports. That is, it's got 2 data bit buses connecting to each cell. And they have separate read and write controls. And the thing that you'll notice by this cell is that its area is dominated by lines. That is, it's got bus lines running through it. It's got control lines running through it, power lines and ground lines. The actual logic, as you're aware by now, is simply the intersection of some lines. So this is sort of a theme in LSI design, that the complexity is not in the devices. The complexity is in the wires. Let's take a look at that cell. Actually, this is a layout picture of 2 cells of the OM2 RAM cell. Again, the array concept that they use here is with horizontal metal lines for power and ground, alternate cells mirrored so that they can share the ground line between them, and then the next one shares the VDD line. The vertical red lines are the control lines, which are essentially gated clocks, which is the load from the B bus and read from the B bus, and load from A and read A, and then there's a phase 2 line that always does a refresh operation on every cycle. I don't want to go into the details of this too much. You can read about it in Chapter 5, but let me just show you how it fits into the overall layout of the OM2 data path chip. The largest array in this chip is this dual port register cell. And if you have a design where you're pretty sure that you have more of one cell than anything else, then that's where you should concentrate your design efforts in getting the size down. And as you can see, it's a large fraction of that chip. And there's a good reason for its size. It really is a fairly highly functional cell. Every word in this memory has the ability to independently read or write either of 2 buses. And that's really quite a bit of logic packed into a small cell like that. And to have a 16 by 16-bit register file like that with 2-port capability, it's not surprising that it takes up some area. What's surprising is that it's that small, actually. Okay, that's the end of the first lecture. Doug will tell you more about the other parts of this chip as examples of some functional arrays in the second part. So let's take a coffee break now.